Yeah, we're going to get started. So today we're going to review again what we were talking about last class for 5-10 minutes, just to make sure we're all tracking with where we're going. And then we'll take the first steps beyond the linear classifier that we've been discussing. It's still going to be a very simple extension. We'll motivate why we need to go past linear classification. I've said multiple times it's not that great, but I'll really give you some good ammunition as to why that's the case, which will then motivate our need to go beyond it. And by the end of this class, we'll hopefully get to the idea of having cascaded nonlinearities included in the classification process as potentially a beneficial idea. Okay, so quick review. Here's our pipeline that we're working with. So in machine learning, we start with training and network. We want to take inputs X with labels Y and come up with a model W that establishes an effective mapping between those two, right? And so to achieve that, to teach a computer to do something, you can't start with nothing, right? We need something. So the first thing we really need is labeled data. We need pairs of inputs X and labels Y. Abstractly, that can be anything, really. It can be very nebulous, actually, at times, like text on a website and knowing the context of that text, right? Or how you're clicking through a computer and the task you're trying to achieve, right? In this class, our inputs are concrete. They're images, right? We're going to work with arrays of pixel values, and they represent data. Here's the example of inputs and labels you'll have on your homeworks, the first two homeworks at least. It's the MNIST digits, handwritten digits, and an associated label. Binary classification, we just have two categories, and the goal of our machine learning network is to tell which image is in which category automatically. The model we want to establish will produce an output Y that is the prediction, a numerical representation of that. And we need a third thing, a loss function, to help us see how well our model is doing. The cost function always, in any machine learning task, produces a scalar value. It needs to be a single number that establishes the efficacy of the network of the task. We then will use that scalar number that is tracking how well we're doing to improve our model during training. Right, we're going to start off with a really bad model because we just guess randomly for a starting point, and then we iteratively improve it by minimizing its value, the loss of value with respect to the weights. Then, once we've done that, and you think you have a good network in machine learning, the next critical step, almost more important than that first step, is to test your network. And so for testing, the second stage, we need uniquely labeled data that is in the same form, generally, as the training data, but it's different. It's not ever been used before. You can't cheat and use it. During training, it's separate. And then we need to evaluate how well we did, right? And so for that, you'll have an out-of-sample loss function, L out, that will establish network performance out of the samples of data you considered to train that model. We can draw pictures like this for the simple case we're considering on our homework where the dimensionality is really small. Generally, it's many, many more dimensions than this in practice, so it's hard to create nice graphical representations. We'll learn some tricks to do that, to help do that with higher dimensional data later in the class. There are tools, but it's a little tricky. This is our linear classifier. All of the assumptions we made boil down to an equation that looks like linear regression with this sign operator, right? That then categorizes the decision. Is it this category of handwritten digit 5s or this category of handwritten digit 1s? It's established by a hard decision with a sign operator, which casts positive values to a +1 and negative values to a -1. Okay, and so this decision boundary is formed via our linear regression process by examining its intersection with the y=0 axis. We went through this several times, so I'm not going to dwell on it. But I'll say that this process of finding this boundary in the linear classifier case, not surprisingly, if you look at this equation, you could imagine solving it directly. And we did that by writing it out in a matrix form and then saying, hey, take that equation, compute its derivative in one dimension, or gradient in the case of w being a vector, set that to 0, and let's figure out the best w, right? So that's achieved via the pseudo-inverse, which we've seen multiple times now. But there's other strategies. That's literally the only case you can use this pseudo-inverse in machine learning efforts, right? So it's like a toy example. We are not ever going to do that again. You'll never do that I hope you'll never really do that in practice once you're hired and asked to solve a machine learning problem. You can try it and it'll probably give pretty bad results, but at least you'll have done something. So maybe in a situation where you have to show your boss you tried something in like really a few hours, you could do it. And the other method I said, instead of doing a pseudo-inverse, is you could try numerical gradient descent. That's also, as you'll see on your homework, problematic and not a great idea. And so really the name of the game is to perform actual gradient descent methods to go ahead and go down the hill with that loss function iteratively. And so that's the beauty of packages like TensorFlow and PyTorch. They create a platform to do gradient descent really easily without you ever actually having to think about it. So what is iterative gradient descent? It follows the pseudocode in this box. You start with a guess of the model that you're trying to figure out, right? Your AI model's weight W, you just initialize randomly, you then update them iteratively until they stop changing very much. While they're still changing a lot, you compute the gradient of your loss function with respect to the weight via some function still to be determined. And then you subtract that gradient times the step size, which can be indexed in the iteration as well, and change its values too progressively. Steepest descent is the simplest gradient descent method to explain. You can essentially evaluate the gradient, let's say numerically, in the case I presented, and then that's just immediately inserted into that evaluate gradient function, right? Steepest descent takes a step in the direction directly of the gradient. In general, that's not the best idea. There's procedures called conjugate gradient descent, which work better, where you take a step towards the side a bit, not going the straightest way down the hill, so to speak, in the direction of the gradient, but deviating helps deal with issues of oscillations. In other words, if you continue to take steps down the steepest part of the hill always, there's many scenarios where you get to the bottom and overstep it. And then you ping pong back and back and back. And so you get these oscillatory behaviors, which are not ideal. And if you go to the side a little, you can loop your way a little bit more effectively, spinning down to the bottom of the hill. If you're interested in that statement where I conceptually explained conjugate gradient descent, but you'd rather learn it in a bit more detail, I'd highly recommend this link here. It's a really good explanation of gradient descent methods for non-numerical computation experts, I would say. It's more of a mathematical, intuitive guide to how different gradient descent procedures work. And it does spend a lot of time just explaining how conjugate gradient descent works. It's designed for computer scientists, I would say, but generally accessible probably to everyone here. So definitely read that if you're interested in knowing like actually how gradient descent methods work in practice. Because when you open TensorFlow and you set your gradient descent method, steepest descent is an option, but you probably shouldn't select it. There's other options, conjugate gradient descent being the simplest of the other options, and this one actually explains how that works. Okay, and then we saw this step size can be determined each iteration as well. It's directly computed from the gradient that you evaluate and the Hessian. So the ratio of the inner product of the gradient and this G transpose HG, for lack of a better word, gives you a scalar value, an optimal step size to take. And that optimality is found by taking a second order Taylor expansion to say, hey, I want to go to this point. And so you can evaluate that point, look at how you need to get there, and the error established in trying to estimate that point can be balanced. The aim is to balance the linear and the second order term with that optimal step size. Okay, so that's the review. Now, what's not to like about linear classification? I list 3, but there's probably more than 3. What do you think is not great about just doing linear classification? In whatever space you're working in, you're assuming there's some separability. That's a linear boundary, I guess you could say, another way to say that. In linear classification, you can only try to separate your data with lines, right? Or planes or hyperplanes, right? Really, in these higher dimensional spaces that will actually be working. Okay, so what are some other issues in the, I would say not just linear classification, but our problem setup that we just established? We only allow for binary labels. And then the third is we have an error function. We selected one. We just said, hey, mean squared error is pretty good. It's actually not that good. Rather, it can be good. It really depends on your data. So the function you choose to establish how well you're doing is really important, and how it's providing you with that single measure of performance. And so if you picked another function, it could be telling you you're doing really bad when in fact perhaps you're doing great, or vice versa. And how do you know which function is better than the other? It really depends on the structure of your data, as we'll see. And I guess I'm telling you this up front and emphasizing this point. When you are doing your final project, or even your homework, but generally your final project, and you're encountering issues, and you're saying, hey, I'm getting, no matter what, I know there's no bug and it's still not working. One of the major causes is actually choosing a poor loss function. And what happens in practice, I've noticed, is people just try a bunch of loss functions, and then one of them works, and they're happy, and then they don't even think about it, which is fine. But in this class, we're going to try to gain a little bit of intuition as to why that's the case, right? So you can go in and pick a better loss function in hopefully in an informed way, or even design your own loss function, right, to get the best performance you expect, given that you've already figured out there's no bugs and you have enough data and it should be working. So why is the loss function important? Here's a simple example. I made this example up, but it's probably mildly related to someone's job at Apple, or it used to be, because they already made this technology. So let's say you work at Apple or whatever, Samsung, because I'm pretty sure Samsung has Face Unlock too. I'm not sure. Face ID. I don't have a Samsung phone. But let's say you work at Apple and your phone does Face ID, right? It unlocks when you hold it up to your face. So what happens in that face with the Apple phone, I know, is it shines a projected pattern of infrared light on your face and takes a picture, right? The pattern helps establish the face's 3D structure, and the picture obviously highlights your face, right? So it looks at the features of your face. Okay, so then what you need to do in that job is from that picture, right? That's the input to a machine learning network. You need to classify it. It's a binary classification problem, generally. You want to say, yes, that's the person, or no, that's not the person, right? And so in this machine learning problem, our input is an array of, let's say, 500 by 500 values in a matrix of between 0 and 255. And our output is a binary decision, which can be represented by a scalar number, +1 being, yes, that is the person, and -1 being, no, it's some bad guy, right? It's someone trying to break into your phone. Okay, so it's exactly the same problem we've just been talking about, put in context. So now there's two ways this output can fail, right? Just in the last problem with the handwritten digits 1s and 5s. And we are going to work with these a lot. These are called confusion matrices. These are ways to establish how well are you doing, right, in your classification effort. Because it's not just about counting how many times you were right versus wrong. You need to know what went wrong, right? And in the binary classification case, there's two ways you can be wrong, and there's also two ways you can be right. Okay, so let's go through those. One way you can be right is the image is you, and the algorithm said it was you. So then you correct, everyone's happy. You can also be right by having the image be a picture of someone else, and then the algorithm says, yeah, that was someone else. There's two cases where you fail. One is when it's a picture here, Y is not you, someone else, but the model says it was you, right? So it's someone else comes up to your phone, shows their face, and then it says, yep, that's you, open up. And then, so that's bad. And then in a different bad way, the model can say, okay, here's a picture of you coming up. I'm not going to open. I think it's a bad guy. So those are the two failure cases. Here is showing. So if it's you can't get it in this case, that's failure mode 1. Failure mode 2 is an intruder it's cut off, or a bad guy, and they are able to access your phone. For you or whoever, an engineer working at Apple, what would be a good cost function to create in this scenario? I'd encourage you guys to think about that. Or rather, let's just say it this way. Which error is worse? False accept. Maybe, I would argue if you worked at Apple, this is worse. Why? Because this is the customer. In theory, if this fails 1% of the time, that's 1% times all the times everyone's doing face unlock every day. So as a user, you're going to encounter this at least once a week if this fails 1% of the time. And you're going to be like, I hate my stupid iPhone. I'm switching to Samsung, right? So I would argue that I'm going to introduce this function we're going to use a lot. It's called a ReLU, or rectifying linear unit. It's just a function that takes a number in and gives you a number out, right? So the ReLU takes any number in, to be between negative infinity and infinity. And then if that number is less than 0, the ReLU gives you 0. And if it's greater than 0, it just gives you back the number. So this is a nonlinear function, right? It has a kink in it, a discontinuity at 0. But it's a very useful function. I'm just introducing it now because you're going to see it a lot. And I'm going to use it to make up a loss function for this problem. What we can do is say, hey, our total loss, we can say, is given by two components. And you can use the ReLU to make those two components, right? If you subtract the label y from the output of the network and it's negative valued, right, that makes it a false accept scenario. And so that's going to be the penalty for the intruder, the ReLU of the output of the network minus y, right? The situations where there is a false accept, right? Because if it's less than 0, you're setting it to 0, right? And so then the ReLU of the opposite case is going to be the false reject scenario. I should have a sum there, sorry. The total loss, ln, is the sum over all the different examples, right, of these two ReLUs added up. And so then I can weight each one, right? And so in this scenario, I'm assuming we're working at Apple. I, as an engineer, would just not tell my boss and multiply this one by 10, probably, because I have a feeling that I'll get fired if I show my boss a demo and they can't get into the phone every time they try it. And are they going to try it on an intruder? Maybe not, but hopefully it works when they do that too. But really, they're going to be carrying it around for a week and just check to make sure they can get in their phone. And if I use this loss function, I'll probably do a pretty good job, right? Because it's really going to penalize that case. If that error happens during training, the error is really going to accumulate. And so it'll really notice those situations where we're having the false rejects, where someone's putting it up to their face and they can't get in. And so what if instead of working at Apple, you were a CIA agent? You were working for James Bond, let's say, as Q, and designing some new phone, right? This would be like 20 years ago, and this technology would be like really James Bond worthy. And you had to do the same thing. I, as Q, would probably really add a huge weight to the intruder, right? Because you don't want anyone to get into James Bond's phone. He'll get hurt, or all the secrets would get stolen or whatever. And if James Bond can't get into his phone sometimes by putting up in his face and gets frustrated, who cares? He has no recourse, really. He still has to do his job as a CIA agent, and he'll keep trying until it lets him in. He can't buy another phone for this, right? It's a custom deal. And so you would choose a very different loss function. You would add a big penalty to the false accepts. And so really what you're trying to do in your machine learning development, if you're working in a problem as simple as binary classification, is to find a loss function, L, and a set of weights, W, at the end of the day, that help really balance and minimize these two cases, these two sources of error. That's really your sole focus. If you can remove all of those sources of error from your test data, right, that's critical. It has to also work with your test data, not just your training. Then you've succeeded. You've made a classifier, right, an abstract model, specifically, as we'll get into, a neural network-based classifier and model that succeeds, right, and works for your application. But it is application specific, right? So you as the engineer need to come with that insight, come with that knowledge and say, this is how I want it to perform. I'm okay with it having false rejects, but I really don't want false success, or vice versa, right? And then the same holds true, not just with this simple classification problem, but also with segmentation, object detection, whatever the task is, you're gonna have multiple types of error, and you need to balance those out in a way that's best suited for your final goal. Probabilistic analysis of machine learning methods is really common. If you read about papers for different machine learning procedures, they often use these expressions of probability to help motivate and or define their approaches. So in the rest of this lecture, we're going to use these as tools to help us understand the cost functions we're using or we've used, mean squared error, what that means. And then we'll use these probabilistic terms to help derive a new cost function. That is the bread and butter of modern machine learning for classification specifically, which is called cross entropy. So we're using the probabilities as a workhorse in this class just to set the stage for the loss functions that we're going to spend our time thinking about and why we do that. In this previous scenario, we have this 2x2 table, which is kind of this very easy, intuitive thing to fill out. And you should, this confusion matrix, to understand how well you're doing with your machine learning task, right? You simply pass data in and add one to each of these quadrants, depending on what happened, right? And then you get this full picture of performance. This 2x2 table should also ring a bell from probabilities. It looks like one of those kind of tables that allow you to examine conditional probabilities, right? So you roll 2 dice or flip coins or whatever, and you line up the 1s and 6s, and you can figure out what's the probability of getting this number on the 2 dice. You add up those entries. So it's a very similar idea. And in those, you're usually saying the conditional probability of getting this, given this, can be examined from this table, generally by summing along the rows or the columns. And so these conditional probabilities of getting a -1, conditioned on the input being a certain value, defines this quadrant of the table, etc. That's a way, not surprisingly, we can measure things from our algorithm. Just like I said, we put stuff into our network and we fill out that table. And that gives us the conditional probability of the results we're getting, y, the output, conditioned on the weights of our network. We have some network, it has some weights, and the inputs, x. So when you see an expression that's saying, hey, this is what a network's doing, the conditional probability of the outputs given the weights and the inputs. That's something we can measure. Our real goal in machine learning, though, is in the space of maximum likelihood estimation, which is a discipline in and of itself, but under the assumptions of a discipline that a lot of people agree on, the goal often of machine learning is to maximize this probability. So it kind of looks like the one above. This probability is the conditional probability of some weights, W, given your inputs and your labels. There is a million models out there, gazillion, and the one that I want to use is, or has a maximum conditional probability given the data that I have access to. So maximum likelihood estimation says your goal is to find the weights W. How do you do that? Well, it's really hard. It's just a mathematical expression. Practically speaking, you can't really solve for this. People have tried, there's all these weird ideas. In situations where you have millions of weights, it's really hard to directly solve for this. And so instead, you can look at these two equations and use some of your insights that you might have had from high school probability and say, hey, those two expressions I can see are probably connected. How are they connected? They're connected by Bayes' theorem. And that's this just equation that take for granted and don't fully understand, but is really important. And it's just connecting these two conditional statements, right? And so if you know one, you can estimate the other and vice versa. And so the whole goal of maximum likelihood estimation procedures is to say, hey, we can measure this. This is just me looking at how well a network's doing, filling out a table. I'm going to use this and try to maximize this because they're connected. If I know some other probabilities that I can estimate, right? General probabilities of the weights, general probabilities of the inputs. Okay, and there's this, it gets a little complicated with 2 condition variables. I wouldn't worry about that. Just take my word for it. This is how it works. Okay, so like I said, the left is what you really want to solve for, the thing circled in red, but can't. It's just an abstract mathematical idea. The green one, the one on the right, is what you have access to. It's what you can just measure by running your machine learning algorithm, filling out that table. Okay, so with that understanding, now we're gonna mathematically derive cost function using this kind of machinery. The cost function we're gonna derive, as you'll see, is mean squared error. And the reason why I'm going through this exercise is to show you what mean squared error assumes, underlying our data in terms of a probabilistic interpretation of our inputs and labels, inputs and outputs. What does mean squared error imply? In maximum likelihood estimation, you can say our goal as engineers in making machine learning algorithms is to ask the question, for what weights W is the probability of my output given my inputs maximized, right? If I can solve that in this maximum likelihood concept, we've figured out our best model. The weights W that maximize that expression are our best model. So we can then take a step and say, hey, we're going to treat every input-output pair in our training data as independent, right? Probabilistic. Is that true? Maybe. Probably not. But we'll just apply that because otherwise this is an intractable problem. And so we'll take a step and say, for what weights W is the product of all those probabilities for each example maximized? Treating them all as independent, you take them all conditioned together and split them up. So now we're going to assume our labels. This is the key assumption we're going to make to derive mean squared error. Our labels, Y, are going to be, for in our first problem of linear classification, given as our classifier applied to the input X plus some random Gaussian noise. Why are we assuming that? It'll lead us to mean squared error is really why. But in general, you need to establish some way to summarize probabilistically what's going on, right? And zero mean Gaussian noise applied to this classification boundary is probably the simplest thing you can really do. To say, oh, I'm trying to classify, but I know I'm going to be off a little bit, and this is how much I'm going to be off. So we're just going to assume that and crank the wheel. So we can take our probabilities of our Y's given our inputs X and weights W and replace it with this Gaussian. That says, probabilistically speaking, the difference between our model and our predicted classification is going to fall off and reduce. The probability will get smaller the further we are away from the boundary by some standard deviation, which is defined by the noise. We're assuming the deviation is. If it's noisier, then those points are going to be distributed more away from the boundary than if not, right? Okay, and so our goal is to find some weights W that maximize this expression. If you're maximizing a product of these exponentials, it's the same thing as maximizing the sum of those exponentials, right? That's just a simple proof from convex optimization, right? If you're maximizing a function, you can go ahead and maximize the log of that function as well, and you'll still do as good a job because log is a convex function. So then what you can say is instead of maximizing this sum of negative square differences, you can minimize and take away that negative sign. So this problem that we started with, that's what's the best weights W for this abstract probabilistic effort, becomes the goal of minimizing the mean squared error between our labels and the output of our model, which is what we did, what we said, what you're going to do on the homework. And so the summary of this little exercise is to say that doing linear classification with a mean squared error metric to assess your loss fundamentally assumes data is Gaussian distributed, right? With under some Gaussian noise spread. And is that fair? Is that the case? Binary classification? Yeah, I would say probably not. Like you saw those red X's and blue circles. Were those Gaussian distributed in that space? Absolutely not. Not even close. So is mean squared error great? It's easy, but for most problems, it's not the best choice. So that's one issue that we can address pretty directly. And so to address that issue of this loss function not being ideal necessarily, or really needing to think about it, we'll also consider the second issue of only having labels that are cast to be +1 or -1, right? Which is something else we were doing. We were taking that sign operation and saying, oh, it's this category or that category. That's another simple thing to do, right? It allows us to execute our code quickly and solve this problem efficiently. Okay, so really what we want, before I get into this, I'll explain conceptually what that sign operator is doing. And you'll see this on your homework. You'll initialize your algorithm, and you'll draw, the computer will draw a line or a plane to separate these two categories of points. And then it'll say, how well did I do? And when you have this sign operator in there, any point on this side is going to be cast as a -1, let's say. If the true label is +1, and it should be on this side, then all of those points are going to be equally bad, right? Because they're all -1 and they all should be +1. And it doesn't matter if a point's right here next to the boundary or way over here. Both of those will be weighted the same. They're both equally bad, and their bad score is -1 - 1, -2 squared. They're 4. So this gets a 4 for the loss, this gets a 4, this gets a 4. And this point, it could be right if you just moved it a little bit over here, right? But that's not accounted for at all. It's just said, that one's bad, that one is a 4 to your loss, and you got to fix it somehow. And so really what we're trying to get to in these next few slides is a measure of, hey, you're close to the line. That's not as bad. Maybe that should be a 1 penalty or 0.5 penalty. Hey, you're really far from the line. This one's wrong, on the wrong side of the line. You're way off. This is like a 10 penalty. I'm just making up numbers, scalars, but it's a much worse. And so you should consider that. Conceptually, that should be a more holistic approach, a better approach to getting that line to do what you want it to do. So to do that, we need to think about this sign function. You can think of this sign operator as just a nonlinear function. And what we really want, that little digression I just went through, is a probabilistic measure of performance. Conceptually, you would say, hey, this point here is probabilistically speaking 1% of the error. If one's way over here, that's contributing to 50% of the error, let's say. And all of those errors should add up to 100%. And so a probabilistic measure is a function that takes some inputs and then maps it to a probabilistic space, as I'll show you. In our sign operator case, we're taking some input, x, or a bunch of x's, x1, x2, for this intensity symmetry, and then we're mapping it via a sign operator to be either -1 or 1. Or you could think of it being 0 or 1, as I wrote here, because that could be a probabilistic interpretation of what's going on. Instead of saying it's -1 or 1, you could say, oh, it's 0% right or 100%, but nothing in between. What a probabilistic measure will do is it'll smooth that out and say, hey, if an input comes in, I'm going to assign it to some probability of being correct. 0 is definitely not correct, right? It's way, way, way far away from the boundary. 1 is or near 1 is I'm sure it's almost sure it's correct. And then there's a space between. You can be 50% sure that's correct, or 10% sure, or 90% sure, right? And so that's what a probabilistic measure does. And this theta function is what's called a logistic function. I'll define it on the next slide. It's going to allow us to do that. Instead of casting our decisions to be either 0 or 1, which the sign operator does, logistic function will give us a continuous distribution can be between 0 and 1, no matter what the input is. The input can be any number, the output will always be between 0 and 1. There's, of course, many functions to do this. Logistic functions, one particular one that's pretty good. And so this probabilistic interpretation of evaluating your algorithm is more natural for most problems. Is it for every problem? No. I'm not saying this probabilistic interpretation really applies globally to every single scenario you might want to consider for optimization. But for cases where, for example, I'm listing a few examples, you're trying to predict the probability that a patient may have a certain form of a disease, given a number of observations, right? If you've gone to the clinic, they generally say, they don't say anything in absolutes. It's more, yeah, this is highly likely. We need to do a few additional tests. And you build on that confidence to get that probabilistic measure up and up until it's as high as it can be, always with the case that they might not be right, and it could be another decision. You can try to predict probabilities of future events happening, right? So if you were making machine learning algorithms for the stock market, unless you are trying to make the next GameStop, where you're saying 100% certainty that GameStop is going to go up in stock. Generally, what you want to say is, probabilistically speaking, I think we should buy this or this one, and then that probability will decrease the further out you forecast. So this logistic function is used all the time in those disciplines as well as in imaging disciplines, where we're trying to probabilistically assign values to pixels, categories to images. And it's this equation over here on the left, e to the x over 1 plus e to the x. Like I said, there's a number of functions available to map any number to be between 0 and 1. This one turns out to be convenient to work with and extremely popular to use. So I tried my best to draw it. It kind of looks like that, but it's a little S-type function. It's symmetric about the y-axis. My drawing doesn't appear to be. But it takes values x that can go all the way to negative infinity. If it's towards negative infinity, the output of the logistic function will be close to 0. It's asymptotically close to 0. And then if they're towards positive infinity, it asymptotically approaches 1. And then really its important part is in between. When the value is in some bounded region, between negative 1 or 2 to positive 1 or 2, it gives you this continuous changing value that hits the y-axis at 0.5. Okay, so we're going to use this. It's also called the sigmoid function. In machine learning discipline, people say sigmoid more than logistic function. So it also has like 2 other names. Just be aware that this function appears all the time. People call it different things. It's, like I said, pretty commonly encountered in this space. So now we're going to use that logistic function, sigmoid function, to rederive a new cost function. So bear with me here. This cost function, right, is what you're going to use more often than not in TensorFlow. If you just download TensorFlow tutorial on image classification, it will use this type of cost function, which we're going to show, this cross-entropy cost function. The cross-entropy cost function is based on this logistic function to tell how good are you doing with your decision boundary. Are you 0% or whatever, 10% sure that that's correct, or 90% sure? That's really what we're after. Not that like it's 100% sure incorrect and it's the same if it's way over here versus here, right? Which intuitively isn't as effective for many problems that you might consider in machine learning. Okay, and so what we're going to do is we have 2 classes. Y is either positive or negative 1, and we want to kind of map that to a probability, right? Or rather, consider these cases not as absolutes, but in a probabilistic sense. Logistic function applied to the input, right? So given some inputs, and they enter our model, right? The probability that y is positive 1, right? If the model gives us a high number, so this is the problem we're kind of considering. Here is our decision boundary. And we have some x's over here, right? This is the positive 1, y equals positive 1 side, y equals negative 1 side. And so if we have our model and a point over here we're considering, and our model, this image maps into the space and is evaluated by our model. The output is like, it can be any value, right? The output of our model between negative infinity, infinity. Let's say this value is like 6, right? And it's on the correct side. It's on the y equals positive 1 side. Then we're doing good, right? So we should reward this and say, probabilistically speaking, this image is on the right side. I'm pretty confident. So instead of just saying, hey, before we were saying, hey, we're taking the sign of this number. It's positive 1. We're 100% sure it's on the right side, for example. Now we're going to say, well, we're pretty sure. How sure? Well, we're going to take that value and pass it to the logistic function. So if it's 6, it's somewhere over here, and the probability is like 0.97 or something. I just made that number up, but it's some high number. It's close to 1. And so for our probabilistic interpretation, that works, right? We just say, hey, take the value of our model and pass it through our logistic classifier. If the output of our model, let's say this image didn't fall over here, it fell over here. These are all zeros, right? Or O's, right? And the X fell over here, right? So the model output would then be towards a negative number, right? Because it fell on the wrong side of the line. So that means the model output is more way over here. It's like -4. Before we were taking the sign of that, saying it was -1, saying that's, now we're not going to do that. We'll pass it to the logistic function. And -4 in the logistic classifier will be mapped to a very low probability, like 0.0 or 0.04. Right? So we're very, probabilistically speaking, not confident that that's good, right? For the y equals positive 1 category. So for the situations where the label is y equals positive 1, this is the expression we'll use for our probabilistic interpretation, right? It's just the logistic classifier applied to the output of our model. For the y equals -1 case, we have to think about it a little bit carefully, and we actually need to flip it. We need to subtract the logistic function's output from 1. Why is that? Well, you can kind of consider the same picture. So this, I'm kind of drew here the same thing I drew over there. So if the network output is large, then it should map to y equals positive 1, right? And we're in good shape for the case where y equals positive 1. So now let's consider this case where the label is -1, right? And so now I'm drawing 1 minus the logistic function. And so for the case where y equals -1, right? If the network outputs a more negative value, then we're doing good, right? It gets towards -1 before we were taking the sign of that and saying, hey, whatever the output is, if it's negative value, we're assigning it -1, so that's good. Here, let's say the output's -3. That's great. It's the label -1. So we're going to say probabilistically, it's almost right. It's 95% sure it's right. And then if the output's large and the label is -1, well, that's bad, right? It didn't do a good job. So we're going to assign that a very low probability that it worked well. So we kind of have a 2-case statement for how we need to assign probabilities depending on what the label is. Okay, and so we can make that even simpler. So this is our probabilistic interpretation of how well we're doing with our model F. And we can add our linear classifier in there now. So instead of just writing this function F, right, we can say, hey, we're doing linear classification. So we're doing this inner product of our weights W and the input X, which is our linear assumption. And we'll also use a property of the logistic function. This is a kind of identity that the logistic function of -a equals 1 minus the logistic function of a. It's just a property of that function. So what we can do is, using this identity, we can take this equation that's defined in 2 cases and write it as a single equation, right? Because for y equals positive 1, right, you put a positive 1 in here and everything's fine. For y equals -1, you put a -1 in here, then you get 1 minus the result. And so this expression is writing this in 1 line. And so then we just, instead of writing f of x, we can write w transpose x. That's our model for linear classification. Okay, so now we have a single expression for our conditional probabilities of our model's outputs given the inputs. it's equal to the logistic function of the label times the inner product of our weights times our inputs. So this is very similar to what we just did. We want to maximize the conditional probability of our labels y given our inputs x and our model w with maximum likelihood estimation. Before, for the case of deriving mean squared error, our expression for this term was an exponential e to the y minus w transpose x squared divided by 2 sigma squared. Now it's just this funny logistic equation. But our conditional probability that we want to maximize, again, is going to be coupled probability. It's not independent. We are going to assume every example coming in that we observe in our machine learning network is independent. That's implicitly assumed in TensorFlow, right? Because the loss function is what we're going to derive. And under that assumption, we can then define all of these probabilities as a product of the individual probabilities of how well you're doing with your network classification. And so we just write this expression. And so that's really what we want to maximize. And so I'm writing our goal as maximizing this conditional probability to get our best model is the same goal as maximizing the product of all of these logistic functions of our labels times our weights times our inputs. All right, so now we just crank the wheel. So if we want to maximize that probability, it's the same as minimizing the -1 times the log of that probability, right? Like I said, if you maximize a function, then you can also maximize the log of that function, and you're doing the same thing because log's a convex function. And so then I switched it to minimize and added a negative sign in there because we did that before too. And so when you take the log of those products of probabilities, it's equal to the sum of the logs of those probabilities, right? And so you're minimizing the average of the log of 1 over this logistic function, right? The 1 over comes from the negative sign being cast inwards. And so this is there's two ways to write the logistic function or the sigmoid function. This is another way to write it. And so we can just input that expression into this equation and crank the wheel. And you end up with this equation down at the bottom, right? I'm not deriving every single step, but what you get is this expression where the loss is equal to the average value of the log of 1 plus e to the, what was inside our sigmoid. Label times inner product of weights times inputs. So it's just some mathematical expression, but this is called cross entropy loss, right? And I'll put it right next to mean squared error loss. So these are the two, I would say, most common loss functions you'll encounter, period, in optimization and machine learning. I can't think of any others that deserve to be in the top two. Maybe like L1 error, which we already talked about before, an absolute difference for like sparsity type optimization problems. That's up there. But these two are really important. And you can see that they kind of share some similar properties. They're both direct averages, right? They're 1 over n times the sum of all your independent examples. That effectively arises from our treatment of all the probability as being independent. And then that's about the main thing they share. But remember, in general, in that derivation of mean squared error, I didn't add in this sign operator that was casting things from one side to the other, right? And so really what mean squared error is very useful for is scenarios in which your data is Gaussian distributed. In other words, when you're specifically when what you're trying to predict is not matching what you think it is, and that mismatch is a Gaussian type error. Generally, you're doing pretty good, and then you get worse when things are further and further away. That's happening with lower and lower probability. And so I think the better picture is when you're trying to form your decision boundary, are the errors distributed in a Gaussian-like manner? In other words, are things close to the boundary and still wrong, and then when they're further and further away, is that dropping off in a Gaussian-like manner? And just from looking at those circles and X's, that's not the case, right? It's very non-Gaussian, I would say, because your boundary is generally determined at a place where there's few red X's and blue circles, and then they cluster. And how far away do they cluster? Well, it depends on the type of problem, right? But that's very non-Gaussian, right? It's like highly skewed error. And so, yeah, that Gaussian assumption is pretty bad. Classifying crisp images from noisy images, right? A noisy image is defined as a crisp image, generally depends on the noise you have, plus Gaussian noise. And so there you have a distribution of images. They're all crisp. They're going to be categorized in a ball of red X's. And then the noisy images will roll away from those in a Gaussian-like manner. And so whatever boundary you draw, the error is going to roll off in a Gaussian-like fashion for that category. It's important to consider the underlying structure of the data. So if you have data that is like a noisy type data, then pretty directly you can try to figure out, oh, it will or will not obey this relationship. But the cross entropy loss generally does a much better job in classification problems, because as you're going through examples, you're really looking at how close are some of the examples close to the boundary versus far away. And you're moving your plane or your boundary accordingly. So if you know there's a bunch of examples that are really close, it'll go ahead and move to accommodate those in a more natural manner than just considering all of the points on the side that are wrong the same. Then it doesn't know, should I move it a lot or a little? I'm not sure. That's kind of the intuitive picture I'm trying to encourage. That sets the stage for this third issue. And so, yeah, this probabilistic mapping, I'm kind of sketching there. The blue is showing a probability of being right versus wrong as dependent on how far away you are from your decision boundary. Well, the first real issue, which we've said many times, but I haven't addressed this lecture yet, is we can only separate data with lines, right? So that's not great, right? We want to flexibly address data, specifically in imaging, because it lies on a very nonlinear manifold. How do you define the cluster of points in a high dimensional space that is the points of, right, MRI scans of someone with a lesion versus not? It's really hard to do. So can we add flexibility by just adding more weights? This is a natural question. So we had a bunch of weights. Let's say we had a classification problem. There's 10 categories. We had a really high dimensional input. We had a lot of weights. And then we'd say, hey, look, it leads to this plane in this high dimensional space. Can we just add more weights to make things better? And the answer is no. If you add more weights, let's say another weight matrix, then you can write out mathematically that the output is equal to the second weight matrix times the output of the first weight matrix, right? And you just get another linear expression, right? In other words, no matter how many matrix multiplies you add, and you're just doing linear matrix multiplication, you'll always be left with a plane, right? And so fundamentally, what we need to do is add nonlinearities. This is what we're going to do the rest of this class. You just have an input, you have a matrix of weights, you then apply a nonlinearity. Then you apply another weight matrix, another projection. And then we'll apply another nonlinearity. Here I'm just showing one. But even one nonlinearity will take a plane that forms our decision boundary, and it'll start to curve it, allow us to curve it. How will it curve? Well, that depends on the nonlinearity we select and the dimensionalities we're working in. But just fundamentally speaking, you need to use some nonlinear, right? No more multiplies and adds, but any other function, right, that you can click on your graphing calculator, pretty much, to achieve this curving. And so what a neural network is, as we'll get into, is really just a sequence of these matrix multiplications and nonlinearities. That's all it is. Here I'm writing an example neural network. It has 3 layers, as we'll say in this class as we keep going. The first layer is defined by this first matrix, W1, times the input. And then a simple nonlinearity we can use is the max operator or ReLU, right? So here I'm just writing max of that comma 0, which equals this rectifying linear unit I defined before. And then we'll take that and multiply it by a next matrix W2. And the output of that will again have a nonlinear threshold. Say we'll take the max of that versus 0, which again is if the value is less than 0, we're setting it to 0. If it's greater than 0, we'll just keep it. Right, so it's a very simple nonlinearity. It keeps half, well, whatever. A large portion of the output is linear if it's positive 0, above 0, and if it's not, it's just set to 0. And then we'll multiply it by a third matrix. So if we assume a model like that, we'll be able to start really curving these decision boundaries, as you'll see, and we don't want to curve them too much. That's the next problem we encounter. So that's what we'll talk about next class, is more about this.